Okay. So we went through the inflammatory process and then wound healing. Does anybody have, I mean, it's probably hard to know if you have any questions since I just threw that all at you, but if you had a question, does anyone have one right now? Yeah, it is typically genetic. There does seem to be some genetics involved in all wound healing. There are some It is possible there are some races that are more prone to keloidal scars, but anybody could get a keloidal scar. You don't have to be African American to get one, but it does tend to be more common in people who have more melanin. I've seen keloids in all kinds of people. And you don't always know how some people say like, "Oh, I'm a bad wound healer," but you never know. It could have just been that one time. Okay, so sure. We're going to I don't see anyone else typing. So we're going to go on now to talk first about infection in general, and then we'll talk about the acquired immune response or the adaptive immune response, which is selective to particular microbes or infections. And that's when things really get a little bit confusing. So we'll try to go slow and get you through it without too much. Um, Although I did want to, wait a minute, stop. I did want to show you a picture of a wound too before we went forward. So I'm sharing my screen again, hopefully. These are examples of healthy wound healing. So this is healthy granulation tissue. It's not gone over the wound edges. It's a little brighter. This is probably a fresher wound where the vessels. So what you're seeing here is the growth of vessels. Here, this is a little bit later in the wound healing process. This wound has contracted quite a bit. It's not as red as this because we're seeing more of the epithelialization over the vessels. So these are both wounds that are healing correctly. These wounds are exhibiting, especially easier to see on this side, something called hypergranulation. So it might be a little bit harder to see if I zoom in here that this wound, the granulation tissue looks kind of bumpy, almost like little blisters. That's not how granulation tissue should be, and obviously this is higher than the wound boundaries, especially here where this lip is, and this tends to be more bloody. This is called hyper granulation tissue, sometimes called proud flesh or exuberant granulation response. And this will hinder wound healing if this granulation tissue is higher than the actual wound bed or grows over that. It'll stop the epithelialization. So sometimes this requires extra debridement in order to heal. Here's some pictures of scarring. So this is showing you how a scar should heal over time. This is obviously the acute wounds. There's still bruising and edema, you can see. And over time, as there's less swelling here, this scar is still not completely healed. But over time, as the wound continues to contract and relax, you see the scar is um, more white and less obvious. These pictures are, this bottom picture here in the bottom left-hand side is a really good example of a hypertrophic scar. That's not keloidal. It's just too much collagen tissue growing above the actual level of the skin. Where the actual scar, if I like follow my cursor, is probably through this, and the scar has actually grown past the original um, incision line. Like the incision line is probably through here. So the scar has actually grown beyond the border of the original wound. So that would be a keloid scar, obviously, on someone that is light skinned. So it can happen to anybody. All right, so infections. Some terminology we'll talk about first that people use when they're talking about infections. You usually talk about infections in terms of their course, and the course is separated into periods of time called incubation, prodromal phase, invasion, and convalescence. So incubation is the time from exposure to the time of the first symptoms that you feel. And the first symptoms might be very, very mild. You might not notice them, which is really the prodromal phase, the initial symptoms that are usually mild. Incubation period in general is a time where people are still infectious, but they don't know that they have it, which is the problem with a lot of infectious diseases, is that you can pass it to people before you're aware of the actual infection. And if you see on here, it says could last from hours to years. Well, and that is definitely true. We know, the influenza incubation period is typically, like a week. COVID is about 14 days. To herpes, which can be 5 to 10 years. So that's always a fun conversation to have with people if you ever work in primary care and tell them that they have a herpes infection. You can't really tell for sure who gave it to them if they've had multiple partners, because it's hard to really tell based on the incubation length of time. HIV incubation period can last a very long time before people have any symptoms, and they could obviously give the infection on if they're not on PrEP. So prodromal is the early symptoms, and then what's happening during incubation and the prodromal phase is there is division of the infectious agent, which will lead to more of the symptoms, and that's when you get to invasion, which is when the body is experiencing the most symptoms from the infection itself, and either that heals and the person recovers, or they die. Pathogens are microbes or types of infections that can bypass our normal defense, and an infection actually taking hold depends on the exposure, the amount of microorganisms that are present, and the person's own immunity. So each infectious organism has a different way of getting transmitted depending on the organism itself. When someone is asymptomatic, are they basically stuck in the prodromal phase? Well, technically, prodromal would mean that they had slight symptoms that maybe they don't recognize until after the disease has taken hold. Like the day before you were feeling kind of tired and that you might have written off, and then the next day you have the symptoms, even like of the common cold. You had like a day where you're like kind of off and maybe felt maybe a tiny scratch in your throat, but you didn't think anything of it. And then the next day you really don't feel good. That would be the prodromal phase. Incubation is the asymptomatic phase. I'm just seeing if Dawn has got a follow-up. But have no symptoms for the entirety. So those are actual just asymptomatic infections. So that's a whole different, they don't technically have a prodromal phase. The actual infection never causes clinical symptoms because the cell division doesn't cause the immune response. So it's a little bit different. So COVID is kind of fascinating in that there are people during the incubation period or the presumed incubation period that will end up as asymptomatic carriers. and we're not really sure what their immune status conveys to them because there hasn't been enough research on that. Or there's people who are asymptomatic that really are pre-symptomatic, that they're going to get into the prodromal phase, and maybe those symptoms are really mild, so they never really recognize that they have an infection and test positive for antibodies later, or they have the full-on horrible symptoms. And part of the reason for people that they have bad symptoms is partially due to their own exuberant immune response. So I don't think we've done enough. Right. And so COVID is kind of interesting. There's certainly not been enough, there's not enough yet to know exactly um, why certain people will present with mild symptoms, no symptoms, or have this full-on horrible course. And part of it has to do with underlying health problems, of course, but it doesn't always have to be that way. There can be people who are basically healthy, and it might be that they have a hyperimmune response. And for some people, it's not just a hyper cytokine response, an inflammatory response, but also a hypercoagulation. There are some groups of people that develop clots from it too. It's a very weird disease. That is for sure. We'll certainly hear much more about it. The way an organism is transmitted depends on the organism itself, whether it's direct contact or indirect contact. If it's droplets, which is the heavier particles, so you have to be closer to a person in order to, inhale that infection. Or if it's airborne, an airborne infection like tuberculosis, you could be 10 to 15 feet away from somebody and get infected. So it depends, on how it's transmitted. And then microorganisms adhere to tissue through specific surface receptors. So they have to grab on to your tissue in order to get in and take hold. That is the reason, the fact that they have these specific surface receptors is the reason that diseases are specific to particular species as well. So most of the time, unless an organism has some sort of mutation that changes its surface receptors and allows for it to infect another species, infections will remain within their own pool. Like there's many dog infections that obviously a person cannot get. But there are sometimes infections that are species specific and sometimes infections that can cross multiple species. And it's sometimes this mutation of surface receptors that brings about a pandemic or a new infection, because there's been a change that allows an infection to leave a certain species and jump to another. Which is, I think, the idea of the COVID infection to begin with, and there's a lot of interesting information, and not all of it is very reliable. That you could go from a conspiracy theories of, to being developed in some lab. I don't know, but it's possible that it was like other SARS coronavirus illnesses started because a coronavirus mutated its surface receptors to allow for species change. Like the bird flu is a type there that was a species change from bird to human. The MERS, which was the Middle Eastern Middle Eastern corona SARS-like illness that occurred, was a change from a surface receptor mutation that allowed a virus to leave desert animals in order to transmit to people. We didn't have to worry about that because we didn't have those It was fairly contained to the region in which it was developed or which it started. What is possible is that there was some sort of species infection change, because coronaviruses are common in the animal world, that allowed it to mutate to travel to people. And so it is possible the original discussion was that in some sort of animal market where there's multiple people around, that a mutation of an illness caused transmission to people instead of an animal there. But it has nothing to do with the cleanliness of the area. That could happen anywhere. It's just mutation of viruses. And the world is open. Any plane can take a disease anywhere. So it's easy for those things to spread. Invasion, the infection has to get through the specific barriers and defenses that and obviously for humans to get through. So it has to get through the mucus and epithelial barrier, and get to the nutrient-filled inside of us in order to replicate. And the main thing for us to remember is that viruses are intracellular parasites, meaning they cannot survive without getting inside our cells in order to replicate. So they are in our cells, which makes them harder to deal with because we have to kill our cells to kill them. Some bacteria are intracellular pathogens, but most replicate outside of cells. They replicate on their own, so they're easier to attack with medications because they're there. They're not necessarily inside of our cells. So clinical manifestations of infectious disease is dependent on the pathogen, what is infected, and certain manifestations are common to most infections because they're part of the immune response itself. And usually there will be some level of fatigue, malaise, weakness, generalized aching, loss of appetite, sort of a slowing of our other functions. And fever is really the hallmark of infection because it's an adaptive response of our body to increase the temperature, because that increases the efficiency of our immune cells for there to be a fever. And in general, increasing the temperature also is harmful to infections, to bacterial agents. So when a fever is present, it is the sign that the body is fighting an invader. So body temperature, we talked about, is the set point is regulated by the hypothalamus, and different pyrogens or fever-causing substances are released, can be also released by the infections themselves. So our classes of microorganisms has to do with the degree of complexity and how we meet them. The two that we're going to focus on most are bacteria and viruses. Bacteria infections are separated into gram-negative and gram-positive bacteria. When a person has, sputum or some sort of culture taken, the first thing they do is try to dye the bacteria with a crystal violet dye to see how the cell membrane takes up this particular stain. And what you're trying to find out is if it does retain the stain, then it's considered a gram-positive bacteria, and that is a characteristic of the bacteria's cell membrane. If it does not retain the stain, and it's a gram-negative bacteria, that is a characteristic of its particular capsule, which makes it more difficult to kill, and is a characteristic that makes it more infectious because there is not necessarily just infectious, but increases the body's response as well because there are toxins inside that extra protein coat. So bacterial infections, bacteria is simple cell structure, but it does like to take substances from our body cells in order to help it grow. So bacteria have released what are called exotoxins, which are enzymes that will damage cell membranes and sort of rob our cells of some of their nutrients, like calcium and fluid especially. So there will be damage or tissue damage from the presence of bacteria because of the exotoxins that all bacteria have. Gram-negative bacteria also have endotoxins, which are contained in their cell wall. And so when the cell wall is broken, there will be an increase in fever, which is why gram-negative infections are usually more severe, even when you first start to treat them, because once you break down or lyse those cell walls, you're going to release endotoxins, which increase inflammation. And that is why gram-negative infections can be more prone to sepsis, because that means potential systemic vasodilation and an increase in fever. So bacteria always produces toxins that also try to destroy phagocytic cells to help protect them. So bacteria has ways to try to protect itself from our immune cells. It can try to coat the antibodies so they don't get activated. It can try to break down immune cells with its enzymes. It can try to suppress inflammation and alter the molecules that express antigen. So bacteria tries to evade our systems or ways to defeat them. And there is obviously a huge problem with bacterial resistance because our body is full of bacteria and bacteria are constantly mutating. So if I take an antibiotic, there might be cells in my own microbiome that are able to mutate to survive being killed by an antibiotic. So I took an antibiotic for a viral infection, and now I've taught my microbiome how to evade that antibiotic. So then when I actually have an infection, it's now resistant. That's one of the ways that that can occur. So I always make people at various points throughout the semester raise their right hand and solemnly swear that they will never force their healthcare provider to give them a prescription when they have a virus, because you shouldn't do that. So bacteria are simple cells, more simple than our cells. They do have DNA that mutates rapidly. They do have some organelles, but they do like to steal from our cells, which is why they release exotoxins. So they damage our cells to rob our cells of nutrients that they would like. And gram-negative cells also release endotoxins that can increase inflammation and fever. And bacteria, as we listed, have multiple ways to try to evade our own immune response and resist medications that we can try to throw at them. Viruses are a much, much simpler structure. They are just a piece of DNA or RNA that's surrounded by some sort of capsule, some sort of protein. And it's classified by whether or not it's an RNA or DNA virus, whether or not it's a single strand or a double strand, depending on the type of virus that it is. And some of these viruses, especially the ones that are RNA viruses, will also need the presence of an enzyme that will allow for backwards translation into DNA, which is reverse transcriptase. So viral diseases are the most common affliction. All the common colds, rhinoviruses, coronaviruses, adenoviruses, respiratory syncytial viruses, those are all families of common cold. Cold sores is really herpes. All the types of hepatitis or liver viruses, HIV. Several types of cancers are caused by viral initiation because it does change our cells' DNA. Because what happens, and we will go through this with certain viral infections, especially when we talk about the respiratory stuff and hepatitis in the liver section is that here we have our, I didn't turn on my drawing. Here we have our cell minding its own business. It has its own DNA inside, and our DNA, like we talked about in the first class, is responsible. It's the code for the proteins that that cell is supposed to make, and then would obviously need to be copied for cell division. So that's our directions for living. Is not obviously related to a virus. And a virus will just be a piece of genetic material with a capsule around it. It's not going to be able to do anything. It doesn't have enough genetic material to keep sustaining itself. It has to go inside of another cell in order to keep growing. So it has surface receptors on it that have to match the surface receptors or surface proteins of one of our cells in order for it to attach to allow it to go inside of our cell. Once that piece of virus gets into the cell, it will uncode itself, meaning it'll get rid of its capsule, so it's just the genetic material. If it's a piece of DNA, it'll splice our own DNA and connect itself into our DNA, therefore creating a mutation. This cell is no longer going to do the work that it's been assigned by its position in the body. It will now become a cell that is responsible for rapid division and replication of the virus, and that'll be its job now. If it's an RNA virus, it will need to be reverse translated into a piece of DNA. So it needs that enzyme reverse transcriptase to become DNA so it can insert itself into our genetic code and make more of itself with its protein around it. And then that has to make its way out of our cell and then can go infect other of our healthy cells. So the intracellular parasites attach and bind to our host cell, penetrate the host cell, release their genetic information, and then use our genetic information to make factories for themselves. And so that's the same picture of the stages of a viral infection. Gets in there, unpacks itself, gets into the DNA, packs itself back up, and leaves. So it's much harder to get at the viral infections because they're inside. So the immune system has a way that it primarily deals with bacterial infections, especially through the production of specialized cells that make antibodies to deal with bacterial infections. That's our immune response, although we know that bacteria are extremely good at evading a lot of our own immune responses, and therefore medication is needed to get rid of the bacterial infection. Viral infections, because they make their way inside of our cells and then divide and bud off and then go find other cells, are a little bit harder to treat in terms of medication because we have to get at them. And if they're inside our cell, we don't want to destroy our own cells. So we can try to get rid of some of the virus particles, and our own cells could destroy virally infected mutated cells. And we can take antiviral medications in certain instances, and what they're doing is trying to shorten the course of the viral infection, but they're never really curing it. And most viruses will become where you don't have symptoms, but some viruses will remain within a certain population of your cells, which is how they can initiate cancer later on. So we have to understand, because they cause different symptoms, but we also have to understand them because they initiate different responses within the immune system, which sometimes can account for some of their symptoms, depending on what type of infection it is. So now we're going to move on to our last section, which can get a little intense. and that is the adaptive immune response. So this is our third line of defense. And in this case, we're talking about infections. So the infection got through our mucus and epithelial barriers, got through our innate response, the inflammatory response that ends with neutrophils, macrophages, and natural killer cells. And now we have to make the link to the adaptive response to try to develop a more targeted, sensitive strategy to get rid of this infection. It's beyond the innate system. The first thing to discuss is the divisions of immunity. So we talked about innate immunity. That's the first and second lines of defense. Adaptive immunity can be further divided into naturally acquired immunity and artificially acquired immunity. Naturally acquired means that first you have to know what the end point is of immunity, of acquired immunity. So if that system has been activated, the end result is antibodies and cytotoxic T cells. That's the end result of acquired immunity. I can receive antibodies naturally, passively, like I didn't have to make them, they were given to me, or I can naturally get antibodies because I went through an actual infection. So I could passively receive antibodies through breastfeeding or my time in the womb through the placenta. I'm given antibodies from my mother. Or I developed them because I activated my own acquired immune system because I developed an infection. So that's natural. Artificial acquired means that either I passively gave antibodies, but in this case, it wasn't because I didn't get them in a natural way. I didn't get them from my mother. I got them because somebody made immunoglobulin or antibodies in a lab and infuse them. So you can give people immunoglobulin if you're concerned. You could give someone hepatitis B immunoglobulin if they didn't retain immunity from their vaccine and they had an exposure. I'm trying to convey parts of the immune system to them without them actually getting it themselves naturally. Artificially acquired adaptive immunity is the basis of vaccinations, of immunizations. If I introduce a modified version of an infection that's close enough to the original infection, then I can cause the body to create the end results of acquired immunity. I can trigger the body to create antibodies and cytotoxic T cells to be in reserve in the memory of this person so that if they're ever exposed to the infection again, they won't have symptoms because they'll have the second immune response, which will make more sense when we talk about it. So when you're giving somebody a vaccine, you're exposing them to something that's similar to an infection, but that actual vaccine doesn't stay in the person's body. What stays in the person's body is their immune response to the vaccine. You've sort of created a file folder to be used later, which I think is a good thing to explain to patients because that's part of the reason why people can be nervous about vaccines, because they're thinking that there's this medication that's going to be in their body for years to come. But the vaccine itself is long gone. It's the immune response that was created that we're keeping. So these are the characteristics of the adaptive response. It works with inflammation because the inflammatory process is what sort of brings the adaptive response over. They kind of are connected. It's important. It also is able to recognize foreign versus or non-self substances, but so was the innate immune response. It just wasn't as specific. It had those toll-like receptors that were very simple. It just noticed that it wasn't itself, but it couldn't tell you exactly what foreign object it was. The adaptive immune response provides a memory, which is one of the most important parts of it, and that memory conveys long-term protection upon subsequent exposure. But it's a slower response than innate response because it has to be built up. So it's selective. So it's not just self versus non-self, it's selective. I know this isn't me, and I actually might have encountered this before I can tell you exactly what it is, and therefore can be a stronger response. So the end products of adaptive immunity are the cytotoxic T cells and immunoglobulins. That's the parts, the working parts. So how do we develop these cells? Where does this all start? Well, first we have to develop T and B lymphocytes. So the natural immune response is those granulocytes, neutrophils, and monocytes. And then one type of lymphocyte, the natural killer cell. The adaptive response is two populations of specific lymphocytes. The T lymphocytes, which are in charge of cellular immunity, and the B lymphocytes, which end up being the end result is the antibodies. And each individual T or B cell, a mature T or B cell, will recognize only one particular antigen. So you, in your body right now, have the potential to respond to millions of types of antigens because you have this population of lymphocytes that could recognize a particular antigen. I kind of think of it as like you have this whole file cabinet of file folders that respond to different antigens. And you developed these pools of resources during your infancy. In the first year of life, your body developed something called clonal diversity. It was trying to grow different clones that could represent different antigens in your bone marrow and in some of your specialized lymph cells. So it's hard to wrap your mind around sometimes to think of that. So you, clonal diversity, or this development of these different file folders, or the development of the ability to respond to millions of types of antigens, occurred in primary lymphoid organs, especially during the first year of life. That involves the maturing of the B and T cells in primary organs, and then those mature B and T cells migrate to secondary lymph organs. And when these cells are presented with a particular antigen, they will interact with a T helper cell, which is kind of like the secretary. It goes through the file folders and finds the correct clone to allow for differentiation into the specific type of T and B cell that we want. So the concept we're talking about here is clonal diversity versus clonal selection. My lymphoid stem cells produce multiple types of lymphocytes, B and T cell lymphocytes. The T lymphocytes, those different clones were produced was produced in the thymus gland in your first year of life. Your thymus gland has since atrophied and can't be found because after we've developed all our clones of T lymphocytes, those cells left the thymus and went to the spleen, especially, and other lymph nodes. So they're there for us when we need them. The B lymphoid stem cells created the production of all the different types of B cell lymphocytes, and those have migrated mostly to our lymph nodes and are there and ready for when we need them. For when they are presented with specific antigen presenting cells, so they can differentiate and copy into a specific clone that will affect the bacteria or virus or whatever we're dealing with. So I'm going to take a short break right here because that's usually hard to digest, to give you a second. So it's 8:40, so we'll go to 8:50, and then we'll kind of touch through it again, explain the difference between B and T cell immunity. So I'm going to pause, and we'll return at 8:50. Okay, so how's everybody doing? Any any questions so far? We're almost done. Just 40 minutes left, so well, that was very Midwestern of me, wasn't it? Oh, Noelle is typing. Mental overload. Yeah, that's pretty normal at the end of this class. So let's see. So we left off talking about how the body accumulates different clones, or a large amount, or you could, if clones is confusing to you, you could even say cell lines of B cells and T cells that can respond to millions of types of antigens. And that occurs firstly in the bone marrow. Some of that further differentiation into various types of B and T cells for T cells occurs in the thymus, and for B cells occurs in the bone marrow. And when those different cell lines develop that can respond to antigens, they move on to the spleen and the lymph nodes, to our secondary lymphoid organs, in order to be available if needed, if called up because a particular antigen has breached the barriers and has come into the body. So humoral immunity is the B cells. These B cells eventually will further proliferate and differentiate into antibodies. Their particular job is to protect against bacteria and viruses. Cellular immunity, that's the T cells. They differentiate to protect us against viruses and cancer. They have minimal to no job in terms of fighting bacteria. They are trying to protect us when our own DNA becomes mutated. That's their endpoint, is to recognize that this cell needs to die because of that. So humoral and cellular immunity work together because they both develop to provide immunity, and both of these types of cells, both the B cells and the T cells, have the ability to leave a memory of their activation, which makes the ability to respond much stronger, faster, more efficient next time around. So humoral immunity is B cells and circulating antibodies that directly inactivate microorganisms or help activate inflammatory mediators that will take care of microorganisms and protect against bacteria and viruses. Cell-mediated, or T cells, are kill directly by attacking viruses and cancers. So they kill their target. So how do we get this process started? How can we get this information to secondary lymphoid cells to tell them in their places in the spleen or the lymph nodes that there's an infection that they need to respond to? That's what we need to figure out now. And the way that occurs, partially, especially, is through the inflammatory process. So when we first drew that picture where we had that edema, and because fluid left, as well as proteins and neutrophils came down here, and they engulfed foreign matter and bacteria. They spilled that information essentially into the tissue space, and that got drained away in lymph channels. Some of that information can then make its way into lymph nodes, which is where they can be in contact with the different types of B and T cells in order to generate that response. So that's one way to get there. The other way to get there is to come in contact with T helper cells, because those are the ones that help initiate the acquired immune response. And in order to do that, we have to present antigen to those T helper cells. And there's two ways that that occurs, and it is different depending on if it's a bacteria or a virus, because we know that bacteria live differently than viruses do. Bacteria are their separate structures. They just happen to cause collateral damage to help promote their lives, but they're separate, whereas viruses do most of their work inside our own cells. So they're different. So if I have a bacteria here, it will get engulfed by a macrophage through the process of phagocytosis, and that macrophage will then, while the bacteria is inside the macrophage, it'll interact with the macrophage's lysosomes, those organelles that have the enzymes in it to chop up the foreign material, in this case bacteria, into little pieces. The macrophage will then create receptors called MHC, or major histochemical receptors, MHC2 receptors. And then the pieces of antigen will be presented on these MHC2 receptors. And this antigen, this macrophage, becomes what's called an antigen presenting cell. It has taken in bacteria, broken it up into pieces, and is showing it to get help, to try to enlist the help of the acquired immune system. So a T helper cell is the best cell for this job. It will say, oh, look at that. There's an antigen presenting cell showing me an antigen. I will help you find the correct cell line. And in this case, there will be some cytotoxic T cell activity, but the most exuberant response to bacteria will be through the B cell line. So that T helper cell will help that macrophage that's presenting antigen connect with the correct B lymphocyte that matches, because we want the right B cell to match with this particular antigen. And then that's great, because when we find the right B cell, then we can tell that B cell, it'll go through particular differentiation, which turns it into a plasma cell. Why is it called plasma cell? I don't know, just to confuse us, because it's in the bloodstream, I guess. This plasma cell is the actual cell that then is a factory for antibody. And we have created this antibody, which will then attach to antigen to neutralize it or help tag it for destruction by our own other cells of the immune system, like macrophages, etc. So we are helping to get rid of those bacteria. So that's one way we can do it, by using MHC. We have antigen presenting cell that processes the bacteria and presents the bacteria on antigen on MHC2 receptors, and the T helper cell is sort of like the intermediary. It helps that find the correct B cell line so we can create the correct antibodies in response to that antigen. So Macrophages are one type of antigen-presenting cells. There are other types of antigen-presenting cells. Dendritic cells are also other cells that are in extracellular space, extracellular matrix, and other areas that could potentially interact with a bacteria. B lymphocytes themselves that are located in lymph nodes. If a bacteria floats through the lymph channels into the lymph cell and is actually present, the B lymphocyte can then respond to that particular antigen. But for us, we're talking mainly about the macrophage as the way to do that. The other way this can be done, so this MHC2 molecules or major histochemical molecules are presenting outside of themselves bacteria. The other way this can be done is a way to alert the immune system that there's a problem inside our own cells. And for us, we know that that is an issue, particularly with viral infections. So we can use our own body cells can use a different receptor in order to do that. So here maybe is a cell in my respiratory system that has been infected with a virus. Oh, Lordy. I need to get a stylus or something. It's just my fat finger here. So this is a body cell that's infected with a virus. This body cell can actually present a warning signal through an MHC1 receptor to alert the outside environment that it actually has foreign material in it. It has a mutation present, because it could be a virus. So it also could be a mutation that is cancer promoting and is not a viral infection, but it's showing that it's not right to the external world. We learned in the first class that there are surveillance proteins inside the cell, like p53, that would generate apoptosis inside the cell if recognized. This is one way that we can try to generate apoptosis of a virally infected cell or a mutated cell by sending out a beacon light. Hey, this cell is mutated. And in this case, it's mutated because of a virus. And again, we can use a T helper cell will recognize that this cell is calling for help and will find the correct T cell line or T cell clone from those diverse clones. We want to find the specific one so that we can then differentiate into what's called a cytotoxic T cell. That's the type of T cell that actually does the work. So the T helper cell is clearly essential to turning on all of the adaptive immune response. That's how we get to, in most instances, get to the correct B cell lymphocyte and the correct T cell lymphocyte that will kill the cell. It's the specialized cytotoxic T cell that actually does the killing. And it works then by attaching itself to the infected cell and releasing a substance that will then poke holes in the cell and induce apoptosis. So T helper cells help the antigen-driven maturation of B and T cells, the ones we want, the ones that work, and they undergo differentiation, and in this case we get T effector cells or cytotoxic T cells. Those plasma cells, the B lymphocytes that turn into plasma cells, give us immunoglobulin, which is the other name for antibody, and there's multiple classes of antibodies. Antibodies in general are shaped like this. There's a back end, or what is sometimes called the FC. This is the constant. It's the one that binds to our immune cells, so it doesn't need to change. This could bind to macrophages or other lymphocytes or what have you. This end is the variable end. The front end is specific for different antigens. So antibodies work directly by inactivating an antigen, or can sort of clump antigens together, or indirectly affect bacteria and viruses by bringing them towards the immune cells that can get rid of them. That's that information. So there are several types of immunoglobulin. Those were listed right here. G, A, M, E, and D. A is located in mucus as well. So there is immunoglobulin A located in the mucus of the intestines and tears in the GU tract, that it's there. IgE is part of the hypersensitivity response. It's cute. Oh, what's it called? There's a Netflix anime show called Cells at Work. It's cute. I recommend it to help understand. Do you know what it's called, Erica? Then I see Amanda has a question. Cells at Work. Interesting. I'll have to check that out. I'm sure my husband will be really excited to watch that with me. Okay, so Amanda says, does MHC1 only work with T cells and MHC2 only work with B cells? Well, MHC1 and MHC2, no, you're fine. MHC1 and MHC2 both interact with T helper cells, but they do help differentiate and help the T helper cell know what's needed. Because if the MHC1 is the one that's calling for help, then that means the problem is inside the cell, and we need especially the cytotoxic T cells to get rid of it. That's the best way to do it. If the T helper cell, the antigen is presented on an, right, because it's a virus. If the MHC helpers, if the T cell is getting a message from an MHC2, that means it's an antigen presenting cell that's a lymph cell. So it's an exogenous material. And so usually the B cell line is more appropriate because we're going to get the antibodies to get rid of those exogenous substances. So it's still the T helper cell that's reacting to both, but the T helper cell will then, because they're different receptors, will then be able to tell which cell line is really needed the most based on what's needed. Okay, so IgE is more of the hypersensitivity response, and then let's see. Okay, and then our main antibodies that we're concerned with in terms of the immune response are IgG and IgM. IgM is the first sort of one to respond, and then IgG is second, and that response is different depending on previous exposure. So IgM is the largest of the immunoglobulins. It has a J chain that looks like this, and then those are connected to it. It has like pieces like this. So it has these extra receptors so it can catch more antigen. It's the first antibody produced during a response to an antigen always. And this is the one that's synthesized during fetal life. You'll get more of the IgM response over that first year of life, which is why breastfeeding is helpful in terms of a child's immunity, because then you will passively give the antibodies of the mother to the baby while the baby is developing their own ability to do so. IgG is the most abundant class. It's transported across the placenta. It's the most protective. It has the most activity against infections, and there's 4 different classes of it, just to know that you don't have to necessarily know what does what. But why the response, IgG is the one that's classically shaped like this with the FC and FAB. This is the constant, and that's the antigen specific shape. Why this is important to know is it does help you see helps you realize if the patient has been exposed to an infection before, if they, it can, the response of IgM and IgG in a primary exposure and a secondary exposure is different. So the primary exposure means, or primary immune response means, this is the first time that the person has been exposed to an antigen, whether naturally or artificially. So either the person has gotten an infection or the person has gotten a vaccine. They are getting primed. It's the primary immune response to this. So during the latent phase or lag phase, there's B cell differentiation. So it takes a little while. It can take several days for this response to really get into its full tilt. The first one that responds is the IgM, and then the IgG response is equal. So it's not as effective and efficient. When the person gets a vaccine, they are going to have some symptoms of increased production of immune cells because their immune cells release interleukin and cytokines. A patient who gets a vaccine will usually have some symptoms, not always, but might have a headache. They might have aches. They might have a slight temperature increase because that's the job of interleukins and cytokines. So you're feeling the immune response. You're not feeling an infection. The whole point is that the next time, the second response is more rapid with larger amounts of antibody produced because there's no lag. I have this memory, this file folder of the actual differentiated prepared antibody and cytotoxic T cell. So I am good to go. So once I'm exposed to it, I can produce IgM just like I usually did, but my IgG response is humongous. So my first response is it's fine. Second response is great. So oftentimes people who, the common cold, part of the reason why you get multiple infections from the common cold is that those viruses mutate, one, and so it's a different virus that you're reacting to. And unfortunately, your immunity, your retained immunity to those viruses isn't always long enough to be okay. You might retain immunity to a certain variant of the common cold for a couple of years, and then you'll lose that memory. So then your next exposure, you're going to get the symptoms again. But if I get a vaccine to an illness, then I have gotten through my primed response so that if I actually had a subsequent exposure to an active infection, I will have minimal symptoms or none because I got the vaccine. That's the whole point of vaccines. So, and then we talked about cytotoxic T cells destroying viruses by inducing apoptosis, and that's because they connect to the cell through the MHC1 receptor, release perforin, which is a enzyme that pokes holes and induces apoptosis in the target cell. And then eventually, obviously, you want to turn this response off. We don't want this to last forever. So once the antigen activity is decreased, then the T regulatory lymphocytes should be slowing down the immune response. And if that's not present, that's the reason why people develop autoimmune infections. So usually autoimmune infections, and the current thought about autoimmune infections is that they're initiated by a virus and the person has poorly functioning T regulatory lymphocytes. And so that same response is allowed to continue. So here we are. Whew, that's one slide there that is going to go through first exposure, second exposure. And it's going to look at this humoral side and the cell-mediated side. The humoral side is the B cells that turn to plasma cells that get you antibodies. The cell-mediated side is the cytotoxic T cells that get you activated cytotoxic T cells in order to induce apoptosis. So we have our first exposure there at the top. that is engulfed by an antigen presenting cell, which stimulates the T helper cell. So if a bacteria could, there is usually not a lot of activity by the cytotoxic T cells for bacteria because it doesn't work very well. If the APC cell macrophage is presenting to a T helper cell and stimulates the production of B cells, then we'll just go down that side. If it's a virus, some virus might be presented by macrophages and induce the B cell side, or the T helper cell will see that the antigen presenting cell is actually the cell itself, which could stimulate the cytotoxic T cells. So we got our cytotoxic T cells and our B cells. This is the specific one we were looking for. We wanted the ones, the T helper cell is bringing us the particular cell that will work. But now it has to further differentiate into the ones we want. So the plasma cell that gives us the antibodies, or the active cytotoxic T cell that can actually directly kill those intracellular pathogens. So we make a memory of that so that the second exposure, we can go right here. We can get rid of this whole part. That second exposure will stimulate those memory cells that are in the general circulation. They're there. I don't have to go find an antigen presenting cell or find the MHC receptors. I just have these memories floating in the circulation. They'll be like, oh, that's back. I have to start this response again, and I will. And so it can happen much, much quicker. And I don't know why that's there twice. So that's what we're looking for when we give a vaccine, is to get that. Is this similar to an allergic reaction? So no, because an allergic reaction occurs related to an antibody called IgE. And for some people, this is a genetic thing, usually. For some people, oh, I see what you're asking. Well, for allergies specifically, people's mast cells get sensitized, or IgE antibodies attached to mast cells. So we'll talk about that, especially when we talk about asthma, because that's a huge component of asthma. The second exposure thing, unless you mean that subsequent exposures to allergies produce a bigger response, but it's a whole different cascade of events, so I hesitate to say that. Where are T cells housed if the spleen is removed? Aha! So that's the problem. There are T lymphocytes in lymph nodes, but you lose a huge portion of your T cells. So if your person's spleen is removed, their risk of dying of sepsis increases. So it's not like you can't live without your spleen, but it is a dangerous situation for that person to be in. So if you are much more likely to die of certain infections. So they all have to get more vaccines than everybody else. A person with a splenectomy, I would be protecting them right now in this current situation because they are more likely to have trouble responding to infection. They will have a significant decrease in their T cells for sure. So yeah, you can live without your spleen, but it's not desired. I don't want anyone to touch my spleen. That's always good in general because the spleen bleeds, so don't touch it. You should never touch it. Any other questions? So this next case, the next two case studies have to do with the inflammatory response in general and then the immune response. The last thing I want to show you is sometimes the differences in the response can produce different symptoms. So sometimes people that have bacterial infections could have potentially an increased fever response in the beginning and are more likely to have a purulent exudate because remember, the neutrophils are going to engulf bacteria that is outside of the cell itself, and that bacteria, when it interacts with lysosomes inside, will then create that purulent exudate. But viral particles primarily are intracellular, and so that there won't be the same, a neutrophil isn't going to be the cell that neutralizes a virally infected cell. So we don't have that same exudative response in general with viral infections. So that's one of the difference that you can look at. And we will bring that up again in the respiratory unit because viral and bacterial infections present slightly differently depending on which area of the respiratory system you're in because of the way they present as exogenous or endogenous and the immune response itself. So then just looking ahead at due dates, let me get the right sheet of paper by me. I'm going to open up the next case study right now because that next case study is due. And then the next class, the exam will be this similar in its way in that you will respond to questions surrounding a case. Although you'll notice that as the semester goes on, the cases will be a little bit more detailed because they're going to be about specific symptoms. So there'll be more clinical manifestations to discuss. And that's where we're at, unless anyone else has any other questions. Okay, you probably need a drink or something. Let's see, Noelle is typing. When do you anticipate that you'll have feedback from the exam? Well, I hope to get most of those done by tomorrow. Not this evening. Yeah, because we don't have a lot of time, I would like you to at least know where you're at. But it's for sure this weekend. Plus, I don't want to get very behind. Because once I get behind, then this all derails. Yeah, right. But then if you have any questions, feel free to email me. And I did give everyone feedback on the case studies. So you should have that. Yes, you guys have a good night. Be safe.
Thank you.
You're welcome. And then I will get this converted and I'll put it up the same way. It's too much information to put up without making it a YouTube link because it's just too big of a file. So I'll do that the same. So that might not be up again until tomorrow because it takes a little while to convert it. Have a good night, guys.